My name is Jeff Eisenman. I'm the founder of Maverick Applied Science. We started in 1999, and it was very humble beginnings. Me and my home office, basically, and had a part-time moonlighting draftsman. But now we have a very seasoned team of about 15 or so. And pretty much we do work all over North America and international as well these days. So we've definitely kind of found our place. And what's important to us is that we kind of share what we know. An educated user is a good user. The ones that are new to the materials, that's where we see the challenges. So we try to impact that by sharing some of this today. So what I'm going to talk about today is basically the merits and considerations of FRP loose linings for large processing. And this goes into a lot of different areas. We see it very heavily in mineral processing. So we're talking like you hear a lot of discussions about like lithium processing, copper mining, copper processing, nickel, those kind of semi-precious metals. That's where we see it a lot. Also, we see it in clarifiers and things like that we might get into water, not water treatment so much, but more and more wastewater treatment and things like that we see as well. So we've done a lot of work in this. We've seen some missteps, I'll say, in the past. So we wanted to understand those missteps. So we did a lot of research on it, and they basically have come to understand what makes them work, where the issues show up. And so I thought I would share some of that today. And I know we have some folks in here that are be touching some of these different kind of processes. So hopefully this is helpful. Kind of as a general outline, we're going to talk about general view of some of the corrosion protection systems. And then we're going to go in and talk about them and kind of do a comparison of them, kind of where they fit in the process of selecting corrosion-resistant materials. And then we're going to go into applications for FRP linings. We'll be talking about some of the processing and fabrication as well as installation. So when we're talking about corrosion-resistant solutions, this is really kind of your broad group of options. So you have alloy materials. You always have paint coatings as an option. And then we get into heavier coatings. So we're talking about more epoxy-based coatings or other trowel-applied coatings and things like that you might see. And then elastomers like rubber lining has been mentioned a few times. And then also you have basically like FRP, and that can be basically a lining, or you've seen a lot with FRP complete structures as well. But these are generally your options. Kind of my view of things is when it comes to materials is kind of every material has its place and its kind of sweet spot, and there's a range there that they work in. Some of them cross over, but some of them shouldn't. And so so what we try to do is try to find the right place and the right material. And FRP doesn't work for everything, I'll tell you that. There's some places that metals works much better, particularly if you get up to higher temperatures. There's times because of concentrations and temperatures, maybe we start to look to dual laminates. So you kind of everywhere has an operating range, and what we try to do is find that material that is kind of in the middle of that range, or maybe we want to be at the 75% level of what that material can do. We don't want to be on the ragged edge of a material selection. If we see a material that's good up to 200 degrees, well, we don't want to put it in an operation that runs 200 every day, and probably going to fluctuate every now and then and go to 205, 207, things like that. We want to be more like something that operates at 175 or something like that. That's kind of, we want to be in a comfort zone where we know that we're going to get good properties. The corrosion resistance is going to be really consistent. So obviously that kind of challenges budgets. So that's kind of where we want to kind of add that technical input to kind of help that discussion. So to kind of go into a comparison here, so we're just going to kind of walk through here. So talk about alloys, so you're talking about like 2205, Hastelloy, Monel and Inconel and all kinds of other things like that. everybody likes metals because, well, that's what we went to school for. That's what we learned the most about. It's homogeneous materials. There are standards and best practices that have been out there for over 100 years in a lot of cases. Um, the downside is once you get into alloys, they're adding chrome, molybdenum, all these other exotic materials, and they're getting more expensive. Also, availability can be an issue. So that's kind of the trade-off with that. Their alloys can work a lot of different places, but obviously there's different pressures. You always have budget considerations, you have quality, and you have schedule, and that's the kind of the juggling match that everybody has to kind of deal with when they look at kind of material choices. So then going from there, so we're talking about painting. Typically, painting is going to go over carbon steel. Carbon steel is a fairly inexpensive material, readily available. But painting is not going to work good. And we're talking about 2 or 3 coat epoxy systems, say. Um, that, those are going to work well when you have modest corrosion-resistant applications, where it's not submerged in a fluid all the time. Maybe it's dealing with leaks and things like that. Where it's more outside weathering and that sort of thing. Again, it has its place, but generally, I mean, the thickness, you're talking 10 mils to maybe 60 mils thick is a heavy paint coat. So you don't have a lot of material to go through when you're looking at painting. And then coatings, that you're getting into more your heavy applied epoxies, mastics, things like that. And when you get in there, part of the challenge too is that the thicker you get, also those materials, because basically they're like a resin material, so there's no reinforcement in there to a great extent, or if there is, maybe it's just like pumice or sand or something like that. So there's not a lot of durability there, so they tend to not handle thermal expansion well. They chip and crack with impacts, things like that. So again, they have their place, but you have to kind of weigh these things out on what might work best for you. So then we get into elastomers. So we're talking, and broadly we're talking about rubber linings. And if we had somebody with, I guess our gasket people probably know the most about those materials. There's multiple rubbers to choose from depending on services and performance requirements and things like that. But generally, those are, say, 100 mils thick to so 1/8 of an inch to maybe a 1/4 inch, or it's pretty common there. With respect to linings, linings are very dependent on surface preparation, and that pretty much goes across the board. We talk about white metal finishes, and we talk about basically you have to maintain a quality working environment the whole time. So what does that mean? That means that generally it needs to be maybe above 50 degrees Fahrenheit and below 100, and it has to stay clean. We want the humidity probably to be below 75%. Between 50 and 75 is really good. If you're in South Louisiana or South Texas in the summertime, that's really hard to do. So if you have those kind of jobs, there needs to be a QC guy in there literally 24/7 that is measuring humidity and temperature that is in a work environment. Because if you come in and, like we've seen places where they just did a 12-hour shift, send everybody home, you come back the next morning and there's dew collected all over the inside of your tank that was just blasted the day before, and now it has this orange haze everywhere. Well, you can't just go back to work. You need to reblast that thing now because they didn't keep their environmentals up. So all the coatings are that's always a consideration that you need to think about. FRP, the good thing about that is when we're looking at like the rubber does permeate. Sooner or later, if the chemical is on this side, it is going to work its way through and get to the substrate on the back side. And it just depends on what the temperature is, what the chemistry is, of how long that takes. FRP, because of the permeation, assuming that we do a good job in selecting those materials, say like sulfuric acid, we know that based on a lot of case histories and testing, that sulfuric acid is going to permeate about 20, 30 mils deep into a 100 mil corrosion barrier, and it's going to stop. It doesn't continue. You know, in my mechanical engineering terms, all those nooks and crevices that are in that resin, basically they get clogged up and nothing else happens. Now, me and Kevin, or maybe Joy, we'll have a little bit different view on that, but that's the way I look at it. So FRP is really good for permeation, and based on the chemistry, we can define what the thickness needs to be so that we can make safe choices. You know, the downside is that is one of the things that if we're doing linings and it's a bonded lining, that you need to maintain that surface prep, and you need to be very disciplined about how the material is put on. But from a corrosion standpoint, you know, it's very comparable, and I'll show you a little bit more comparable to what you can get out of any alloy pretty much. And so here's some examples of that. I borrowed some of this from my friends at INEO, so I'll give them some credit with that. So Kevin showed something a little bit similar to this, not exactly, but so if we look at just normal, I guess the epoxy vinyl ester resin is kind of what Kevin had talked about before, and then he had the Novolac epoxy. So we're just looking at the epoxy vinyl ester. So for sulfuric acid, it works well for up to 30% concentration and up to 100 degrees C. So pretty high temperature. That's pretty much the high end of process temperatures that we see. Very typical. If you look at for that same range for like 2205 for, you know, duplex, it'll handle 30%, but only to 30 degrees C. So FRP, and this is just kind of I'll say it's a good grade, not the best grade, or most resistant grade. It's going to do far better. And then you're looking at alloys like, you know, C276 and Hastelloy, and it's still not doing that well in an acid kind of service. Hydrochloric, very similar. You're looking at 15 degrees or 15% and 80 degrees C. The point that I want to make here and kind of add to this is if we went from just kind of a mid-grade vinyl ester to the Novolac vinyl ester, you're going to see that it'll handle from, instead of 15, it's going to go up to, I think, 35, 36, 37 is what Kevin pointed to earlier. HCl is a service that FRP is. I've seen FRP tanks that have been in service over 30 years, and I can't say they're pretty, but they're sufficient. They're suitable and still in solid service. When you look at comparing with 2205, you know, really it's marginal at best. You're looking at 1%, and even Hastelloy is not super there. Then you go on and look at the chlorides and salts. Pretty much, you know, that's a sweet spot for FRP. FRP will handle that almost at every temperature for liquids up to 200 degrees C. You know, we see that. And if you look at 2205, 2205 has a sensitivity to chlorides, and it's temperature dependent. So if you're looking at ambient temperatures, instead of 2,000, maybe that might be 15,000 or something like that. But if you're looking at process temperatures like what we might see in maybe a chemical plant, a chlor-alkali plant, or in the FGD system in a power plant, you know, we've seen where they build and they said, well, we want a better material than FRP, so we're going to build out 2205. And we've seen through-wall leaks after like 3 years because they weren't aware of the chlorides at the time, because duplex was like the big deal. But we've learned a lot since then. So this is something that I put together that's a little bit different that I haven't done before. So basically, we've talked about these different material systems, and this is based on our experience. This is what we see based on typical manufacturing practices and typical operation. All those things kind of play a part in service life. And I'll say, you know, operating conditions of these are typically from 40 degrees C to 80 degrees C. And, you know, if the temperatures are lower, you're going to extend the life because that temperature doesn't play as much a part in things. And also with abrasion resistance, which I'll touch on from time to time. The type of the particle, size of the particle, the shape of the particle, all those kind of things play a part in there. But just to kind of set some standards there, so of what kind of this means, because it is a little bit subjective. So for paint systems, generally we see anything from 2 to 5, 7 years. 3 to 5 is very typical. And now I'm talking about like chemical services, and not talking about like painting your pipes and, as far as like just being out in the weather and things like that. Because when companies look at linings, and you're lining a vessel of some sort, it's a process vessel, I mean, the one of the first choices is painting. Well, we can get a good coating on there. We know what it does. Carbon steel is cheap, and we see in the process, it's easy, it fits the budget, but if it's not perfect, if there are thin spots, if there are chips and scratches or anything like that, that's going to be a point of a leak at some point. So that's kind of how that impacts. And then we look at some spray up coatings that may be epoxy coatings. There are spray up systems for FRP as well. Those are much the same application. Generally, they're a little bit more robust, a little bit thicker. They can get them. Sometimes they might have 10% of some sort of reinforcement, like glass beads or something else. Generally, we see a little bit better out of that. Maybe we'll, I would say typically, probably 7 years, 7, 8 years is what we typically see, maybe up to 10 years. But because there's very minimal reinforcement, you see a lot of flexure in tanks from thermal expansion, things like that, and from basically tanks being filled and emptied. Though those shells are always flexing, you may not see it, but they are. And that flexing will actually start to debond and crack and create kind of weak spots in that coating, and sooner or later they show up. Trowel applied, I mentioned earlier, so that's when they're putting on a mastic, and literally they are applying a heavy, it's typically some sort of epoxy material onto a wall. Could be 1/4 inch thick or something like that. These kind of materials, it means very labor intensive. It's very intensive on surface prep and things like that. We find, in the service, it may be putting it in a more demanding service, but we still see about the same kind of service life out of it. So again, like 7 to 10 years is kind of very typical there. And you can always get a little bit more depending on, maybe service prep was really good. Maybe you got a great vendor. Maybe your processes run super stable. You can always get a little bit better, but that's kind of what we see. Rubber linings, 7 to 10 years are very typical. We see a lot of systems and we'll talk to people and they'll say, well, it was really good by year 7. We started to have basically debonds where joints started to peel back a little bit. We started to have repairs, and then every year it gets a little bit worse, because once you lose that kind of fresh surface, it's really hard to get it back. When a fresh blasted surface is the best surface to bond to. You can't produce that good a surface with a hand grinder, and if you try, it's going to hold up for some period of time, but it's kind of like, I'll buy a car and my paint job will last for 15 years, 12 years, something like that. And then maybe I really like the car, so I repaint it. And the repaint job is never as good as that fresh, brand new paint. So if you got 15 years of the first one, maybe you get 5, 6 again before it starts kind of showing up around the edges and things like that. Or you see that the weathering kind of happening where you've got the sun beating down on it and stuff. And any kind of rework, secondary bonding, that's kind of the issue there. So so the rubber lining, 10, 12 years, like I said, we start seeing issues. Something between 5 and 7 is generally where it starts. It's been our experience. I mean, we hear people that say, "Oh, we've got linings for 20 years or something." That can happen if it's in a mild service. If you got a great vendor and everything kind of lines up, it can happen. Okay. Dale talked about chlorine headers and 40 years service. We don't see that. So I like to figure out what they're doing, because we would share that. Yeah. So, but I mean, it can happen, but there are a lot of factors that have to kind of line up for those things to happen. So then we go to FRP bonded layers or bonded linings, And so this is basically, like we talked about, we were showing a rubber lining that's peeling off. We've worked with owners where we'll write specs, we'll have quality guy on site all the time, and they'll blast it out where we're basically doing a test of the surface. So we're actually looking for like a pH value. You want to see that there's no chemistry left in the steel structures. We're checking surface profiles, and then basically we're doing laminate tests to make sure we're doing bond tests and pull tests to make sure we can get a good bond. And then we're saying, okay, now let's go to work. And they'll do it basically in courses, like from top to bottom or around if it were a really big tank. And it's a lot of monitoring, and generally we can get a pretty good job because there's a lot of attention put to it. And generally that's something 12 to 15 years is what we see on these kind of linings. If it were an FRP tank, we were rebonding it and putting a new lining in an FRP tank, we would see generally the same kind of service life. And then we go to loose linings, and we've seen loose linings go much further, and I'll get into that a little bit more as we go along here. But a lot of it is because it's this shop-controlled fabrication to start with. We minimize the amount of hand labor that's going into it, and kind of control the process a little bit more. So when we talk about bonding, so here's a good example of bonding. So this was actually rubber lining after around 10 years or so, and they're starting to have some edges peel up and things like that. So this is where we would basically blast out the lining and then basically get our surface profile. Probably it's going to be covered, and we're going to put a primer down so we can get a bond to the surface. We have primers that literally they'll bond to almost anything. We can bond to concrete, we can bond to stainless, we can bond to carbon steel, and they work great as long as we kind of follow the rules. And then we're going on with like an FRP structural lining after that. So when we talk about loose linings, Kevin kind of showed some photos of this earlier. So this is a panel construction basically, and we've seen these done up to about 70 meters. So we're talking very large structures, and they're highly engineered, and you can see the panels there, and you can see the amount of weld. So if you can think of, if I was doing that all by hand, it would be a patchwork all the way around. So we basically just eliminated probably 70 to 80% of the handwork that goes into this. So we're going to kind of drill down on this a little bit more now. And as I mentioned before, that last one was concrete. I think that was 60 or 68 meters in diameter, so over 200 feet in diameter. We can do it in steel as well. Those tend to be more like 30 to 50 meters probably. Tends to be more typical. And with those, basically, they're putting some sort of waste material in. It can be something coming to the clarifier from, it could be from their waste ponds or something like that, where it's got solids in it. In mineral processing, it's going to be kind of a raw, concentrated aggregate where it's going to have rocks and sand and things like that in there as well, mixed with, like, say, copper sulfate in a copper process. And basically they're letting the solids settle down to the bottom, and that's kind of what that sweeping rake does. And then basically the pure clear material comes over the top. We have these weir plates here where basically it kind of trickles into the trough, and then they cut off kind of the sweet material. Should be cleaner, and then it's further refined after that, just to kind of give you a little insight to that. So what makes them work? So like you've already talked about some aspects of non-metallics, and we've talked about thermoplastic, we talked about thermal sets being like FRP, and thermal expansion is always, it just comes up in the discussion pretty quickly. So to give you an idea, so we were looking at the coefficient of thermal expansion. So you have rubber here, and so this is basically micro-inch by micro-inch per degree Fahrenheit. So you've got rubber here, not surprised that that's going to expand and contract quite a bit. So you got 130. Here's hand layup FRP, and again, this is at process material. So this tends to be very resin rich, about 60% resin to 40% glass. So that resin is what drives thermal expansion. The more glass we have in it, we start to see that coefficient kind of come back. So when we get to filament winding, we're like 60% glass to resin, and that number will go down to 15, 16, something like that. But that's kind of where we're at. But when we compare that to carbon steel, FRP is like 3 times as much as that temperature, and you kind of can see where like concrete and stainless are as well. So just for that reason, you can kind of see why maybe FRP needs a little bit more attention than what you might expect from a lot of processed materials. So here's a kind of a closer look at this lining here. These were these linings that basically the same one that Kevin showed earlier. So this was in Baja, California. So very south, very tropic. Our inspector was here for about 3 years looking over these projects, so really good inspector. So he definitely liked this climate. But he would take temperatures on this at midday, and he would see 140, 150, and all of a sudden, with no pressure, these were expanding such that they were like buckling and moving. So for these, this is part of the design process, is you have to look at that full empty kind of situation, because they had not in some others, and we actually saw panels cracking at the joints. So it's not like you can just buy a bunch of panels, throw them in there, weld them up, and you're gonna have everything work out. So this is kind of where the deal starts. So all these panels here are loose. They're just laid on the concrete. Okay, the nice thing about this that I like is that on the concrete we actually did basically like an FRP secondary laminate for a corrosion barrier, a secondary corrosion barrier. So you basically had like secondary containment, and we had a leak detection system in it as well, where if there was something that leaked underneath, it trickled out the bottom, and we could get a telltale, and we could see exactly what area it was coming from, and that might be from a quadrant, or maybe we could locate it to a few panels, but that's something that we were able to do with this. But it's basically anchored in the center, and then all that expansion drives out to the outside to this corner transition, and this is where all the stress is. And you can see here 4,500 psi. Stress is pretty high for FRP. This has to be monitored quite a while, and this is free as well. The only place this is pinned is basically at the top here. So basically you have to plan it. That knuckle has some design features. We have to design the laminates for the knuckles to work. But again, if the engineers do their job and we have all the right inputs, or the complete inputs, I'll say, we can pretty much design almost anything. It's whether or not the end users in the room can afford it, but we can definitely make it work and make it safe. But just to kind of give you a little bit of idea, and some of the things that we have done to kind of understand this and work through the issues that we saw when we were inspecting these is there's a coefficient of thermal friction effect here, where I showed you it in concrete. Concrete, it's very rough, it's going to bite. It's about the liquid loads pinning it down. So on the surfaces, you need to know basically what is that coefficient factor. So we actually basically made a sled here with an FRP panel on the bottom, made to a certain roughness on one side, and actually did friction testing. So we basically pulled it across a defined steel plate, basically like what we would see in the process. We looked at what the friction was, and each of these plates represents basically about a foot of liquid. So we looked at it at different liquid levels as well, so that we could kind of understand all the aspects of what was going on here. And this is what a dynamic friction test looks like. You go from static here, and you're pulling, and where it resists, and then you hit a point, and then all of a sudden it gives, and you go, and basically you see this kind of effect after that. So this is kind of what a result might look like. to give you an idea. So basically we took that, we modeled it, we looked at it at different diameters and levels of liquid. And so here we have it, you'll see here. So this is empty, and this is with 9 foot of liquid. And so when it's empty, I showed you all that thermal expansion here. So by the time it gets to the outside edge and it's hitting that corner, it's expanding, approaching 3/4 of an inch. When we start to put the liquid loads on it, well, because we've worked out friction factors and looking at it, basically that liquid is helping us. So we find that basically that liquid has reduced it from almost 3/4 of an inch to less than 1/4 inch. So that's the amount of engineering required to go into this kind of process. And this is a further representation. So each of these represents basically going from no liquid to, I think it's 3 foot, 6 foot, 9 foot, 15 foot. So you can see basically the greater the liquid load, it's kind of like soil bearing for buried pipe, where basically the soil is pinning the pipe down so the pipe doesn't expand and contract when it's underground. So it's similar kind of concept. So this is kind of what we have done, and basically we've got to a point where we understand it. We know kind of where the limitations need to be, and here you see this is with that liquid load, and you can see the stresses are under 3,000 psi now. Some of the keys are fabrication. Because these are so large, they have to be like super flat. We don't want the edges curling up, because then you're basically creating a lot of stress points and things like that. So we work with a lot of vendors and kind of figured out what kind of how they need to be built, what the control points are. You can see we can actually achieve a really nice flat product, which is kind of rare, difficult, I'll say, to get that kind of stability out of FRP. So these are some of the launderers, those troughs that I showed you kind of around the sides. They're very labor intensive hand layup. So that's a lot more kind of classic FRP hand layup material there that goes into that. All these points are something that we're inspecting and making sure that we're hitting the quality points. And because when it goes together, the seams need to match, everything needs to come together well. We don't want any surprises. If you have any edge curls up, or like we get those waves that I showed you, you need to understand kind of what the impacts of that are. And we've kind of framed our spec, so we don't want to kind of go awry from that. So these still require quality. And here is an example that we have to have a lot of site QC. So that we're bonding here to the this is kind of at that center point that I showed you, and you'll see some kind of the location of that a little bit more. Because there are solids in there, we have to use abrasive materials toward that center point, because as the rocks and the heavy solids are coming through, it is kind of a pinch point where you're getting a lot of impact in that area and a lot of wear. So we tend to do silicon carbide layers there so it'll be more resistant to impact, and because some of the rocks can get quite large as well, to kind of help the wear on that as well. So this area is actually like bonded directly to the steel, to the concrete, whatever it might be, so that it kind of, when I talked about that anchor point in the middle, this is kind of where it sets. And then from here, you're going to basically this is kind of the start of the panels that you see here. So this is all bonded to the steel or the concrete, and then our free floating panels kind of go up from there. You can kind of see them doing the joints there. Obviously, these are big processes, big equipment, needs quality supervision, need to understand the materials, need to understand the details of that. And obviously, QC is a big part of that. This is kind of what the panel construction looks like. And I guess to the kind of the point of this one, here's a better look at the kind of that center point when I'm talking about that, to give you an idea of what it looks like when it's completed. This rake here that we see is kind of pushing the rocks around and kind of bringing them down. This can be FRP lined, it can be rubber lined, it can be alloy. Lots of choices with that as well. This is Jaime. Jaime was the guy out here on the site for like 3 years. He's a good man. What I wanted to kind of present, we've talked a lot about like bonded linings, and this is something that we have seen done, I'll say. Seen it done well, we've seen it done not so well, and basically we have dug into this over about 10 years and got to a point where we understand it. We're actually working with engineering companies now to specify these because they are a very good option. Because of the panel construction, it minimizes the hand layup time. So, the hand labor is kind of an issue to challenge the quality, I'll say. Also, the efficiency and time of installation. It's speeding up the time of installation as well. So it can be a very good option there as well. And because the panels are made in shop, generally the quality of those are going to be better. So your maintenance is going to be lower. Your resistance is going to be lower. It's kind of like that, brand new car versus the used car. And so it can be a really good option when you get into these big materials. I know everybody doesn't have processes this big, but they're changing. We're getting into some of these lithium processes, and like I said, we're doing clarifiers in other places where we're seeing just everybody wants more and faster, and so this is starting to come into play. So I kind of wanted to present that here.